So in our example problem here, what you're doing is developing a motorized wheelchair, kind of similar to a Segway, that allows a person to be supported in an upright position and operate the thing by moving around. But you want to make sure that the forces aren't too large. You want to make sure that this is a safe product. So you're tracking the velocity, and at a certain time, 31 seconds, you calculate the velocity to be this number right here. And then you have the wheelchair operator go ahead and brake and turn sharply exactly at this time. And then once that maneuver is done at t equals 35 seconds, you go ahead and measure the velocity as this vector right here. Now you know that the mass of the wheelchair plus the rider is 280 kilograms. So the question that you need to figure out is, what was the net force exerted on the chair by the ground during this time period? So the first thing we really need to do is define our system. And it makes the most sense to include our rider in the system. The reason being, if you don't include the rider, then there's going to be an additional force on the wheelchair due to the rider. By including the rider inside the system, that actually makes the problem a lot easier. So the only things then exerting a force on the surroundings are the earth and the ground. The reason we have the earth separate from the ground is that this right here is referring to the gravitational attraction between the two. The ground doesn't necessarily have to be the earth. It could be the floor of a building. It could be something else. But that gravitational force is definitely due to the earth. Now, one of the first things we want to do is try to sketch out what the problem looks like. It doesn't need to be anything fancy. As you can see, my artistic skills are rather limited. So here's my little Segway type wheelchair going in this direction and then turning and ending up in this direction. And I've also drawn a motion diagram indicating the path taken by this. So this gives me a visual idea of what's going on. It's important that you do these steps because we're very visual creatures. That's how we evolved. And just going from a word problem isn't necessarily the easiest thing for us to do. By translating this thing in steps from word problem to physics problem, we can help ourselves quite a bit. Now, after we define the system and the surroundings, we need a free body diagram. And here I've drawn a top view. And in the top view, really the only force on the chair is due to the ground. That's ultimately what we're trying to find. Now, I also need to list all of the known and unknown quantities, and I want to give each one a variable name. So we've got our mass, the two times, and the two velocities. So in this problem, it's pretty obvious which is initial and which is final. And I've labeled them as such, with I for initial, F for final. And the only thing that I don't know is my net force. The reason we have you go through these steps is that sometimes when you get to more challenging problems and you're not quite sure what to do, if you at least start off with these steps, it gets you going. It kind of gives you something to do, and it helps you figure the steps out as you go along. So now that I'm looking at these numbers right here and realizing which equations I'm going to need, let's see, I will probably need to use the equation that delta P is equal to F net delta T, and P is equal to gamma mv. All right, so let's kind of compare these equations with what I know. I've got a mass and two velocities. So mass and velocity will give me a momentum. The fact that I've got two of them is going to give me two momenta, an initial and a final, so I can find my change in momentum. I have a t final and t initial, so I can figure out my change in time. The only thing that I'm missing then is this F net right here. So that's exactly what we need. Now I can go ahead and I can write down a strategy. My first step is going to be to calculate a delta V, a change in velocity. And from that change in velocity, I can then find the delta P. And then from that delta P, I'm going to make use of the fact that F net is equal to delta P over delta T. Now, one simplifying assumption I can make is that this one simplifying assumption I can make is that since my velocities are much, much less than the speed of light, that means that this gamma factor right here is going to be roughly 1. And so on the next page, let me write down a simplifying assumption. I'm going to assume that since all the velocities, all the v's, are much, much less, that's what these two less than sign mean, much, much less than c, then gamma is approximately 1, which means that p approximately mv. You don't want to jump to this equation right here because this equation isn't true. This is an approximation only. You always want to start off with the relativistic equation, p equals gamma mv, and then as you're going through the problem, see, well, does it make sense for me to go ahead and make this simplifying assumption? All right, so now I can go ahead and start calculating things. Let me find my change in velocity. So my v final, going back here, is -1, -0.2, -1, -0.2, comma 0 meters per second minus, and v initial is -1.8, comma 0.9, comma 0. So that change in velocity, let's see, -1, and this negative, with this negative here, is going to give me a +1, so this comes out to be 0.8. -0.2 minus 0.9 is -1.1, and then 0 gives me 0. So delta P is equal to m delta V. I've actually taken a little bit of a shortcut here because this P contains P final and P initial. This delta V contains V final and V initial. So I've actually kind of combined two equations into one to give me a little bit of a shortcut here. So we've got 280 kilograms times 0.8 comma -1.1 comma 0 meters per second. So delta P ends up, let me go to my calculator. Let's see. So 280 times 0.8 is 224. 280 times -1.1 is going to be -308. So 224, -308. 224, comma -308, comma 0 kilogram meters per second. Incidentally, the kilogram meter per second is the unit of momentum. So that's good. As you're going through the problem, you want to be checking and making sure that your units are making sense. So the final step then is that F net is equal to delta P over delta T. So it's going to be this delta P that I had up above divided by, let's see, 35 seconds minus 31 seconds, which is going to be this divided by 4 seconds. And so let me just go to the next screen to write down my answer. It's equal to, go back to our calculator, 224 divided by 4 is 56, and -308 divided by 4, -77. So 56, comma -77, comma 0 kilogram meters per second squared. Turns out kilogram meters per second squared is actually in Newton, so this is 56, comma -77, comma 0 newtons. All right, so there's my answer. Make sure you always highlight that. And then we actually need to check our answer. And we're going to do two things. The first thing is to look at the units. And we typically do that by going back to the last equation that we had, which is going to be, say, this one right here. We've got kilogram meters per second over seconds. Make sure that works out. Kilogram meters per second over seconds. And when we have fraction divided by fraction, that's the same as multiplying by the reciprocal. Kilogram meters per second times 1 over second is kilogram meters per second squared, which is the definition of the Newton. So units check out. We also have to see if our answer is at all reasonable. We want to compare these things to real-world numbers. And on your equation sheet that you'll get on the assessments, on the back I have a number of real-world values. So two that kind of caught my eye. One is that 1 pound is roughly 4.4 newtons. And a 180-pound adult is approximately 800 newtons. So if we look at these forces up here, well, both of those are roughly 10 to 20 pounds each. So this definitely seems reasonable. 10 to 20 pounds is a lot smaller than 180 pounds, a lot smaller than the weight of a person. So this seems reasonable because 10 to 20 pounds of force is small enough to be safe. And there you have it. We have a complete solution, and hopefully that was helpful.